Among all the available processes to produce syngas, such as hydrogen in a large scale, the most established and commonly used process is steam methane reforming, or also known as SMR. For our plant designed to produce 30,000 tons per year of hydrogen with a purity of 99.9%, we have chosen SMR as our system. The conventional SMR process used in this industry consists of two main steps. The first step is endothermic SMR. This reaction is a chemical synthesis reaction that produces hydrogen from a natural gas, and it will react steam with methane in the presence of catalyst. This endothermic reaction usually takes place at a high temperature, around 700 until 1100 degrees C. For the second step is exothermic water-gas shift reaction, or WGS. It is an exothermic reaction that reacts carbon monoxide and water vapor to form carbon dioxide and hydrogen. And for this reaction, it will run at a lower temperature, around 200 until 400 degrees C. As mentioned above, steam methane reforming is a catalytic process, and it uses active metals to increase the rate of production because catalysts can speed up our reaction. Based on article Kinetic Study and Modeling of Steam Methane Reforming, catalysts such as nickel and ferrum were added in aluminum oxide form to speed up the rate of reaction. The catalyst that we decide to use in our plant design is 18% weight percentage of nickel aluminum oxide. The reason why we choose nickel-based metal because it can withstand a very high temperature until 1100 degrees C reaction, and it exhibits good mechanical strength. The type of reactor that we have chosen for our plant design is packed bed reactor, or PBR. The advantage of using packed bed reactor is the higher conversion per weight of catalyst than other catalytic reactor. The conversion is based on the amount of solid catalyst rather than the volume of the reactor. According to Abbas, Dupont and Mahmoud, for a steam methane reformer with a nickel-based catalyst, the optimal operating conditions are in the range of 700 until 1100 degrees C with the pressure of 1 atm. For our plant design, we have choose our operating condition. For operating temperature is 700 degrees C, the operating pressure is 1 bar, approximately 1 atm, and steam to methane ratio is 3.12. For the optimum operating condition for water-gas shift reaction is around 300 until 400 degrees C. For our plant design, we have choose our operating condition. That is, for operating temperature 350 degrees C, operating pressure is 1 bar, and the steam to CO ratio is 3.12.
So right now, I'm going to talk about the overall system design of the hydrogen production plant. So based on the process flow diagram, the PFD, CH4 enters the SMR reactor and reacts with H2O to produce CO and H2. So the outlet gases of the SMR is then sent to the WGSR, where in the WGSR, CO will react with H2O to produce CO2 and H2. So in the outlet of the WGSR, there are actually 5 gases, which are CO, CO2, H2, CH4, and H2O. So since we are going to get a purity of 99.9% of hydrogen gas, we have to eliminate the undesired gas one by one through separation units. So first, these outlet gases of WGSR are sent to the CO2 absorption unit, where only CO2 will be removed. But the percentage of removal of CO2 at the absorption unit is not 100%, means it is impossible to achieve 100% of removal of CO2 at the CO2 absorption unit. This means that at the outlet of the absorption unit, there will still be CO2 remaining, although the amount has been reduced. So this outlet gases of CO2 absorption unit is then sent to the PSA unit, where in the PSA unit there is actually around 10 units in which undesired gases will be removed one by one, and at the end you will get a final product of 99.9% hydrogen purity of hydrogen gas. So the kinetics data of the reactors are actually very important, especially when determining the sizing of reactors that is suitable for the production of 30,000 tons per year of hydrogen. So right now I'm going to show the methods I use to obtain the kinetics data of both reactors, which are the SMR and WGSR. First, derivation of equation is performed by using the Moore balance of packed bed reactor, stoichiometry, and Red-Law equation. So from this derivation, a final equation is obtained, and that final equation is ln dW over FA naught dx equals to negative alpha ln Ca minus ln K. So from this equation, the reaction order alpha and rate constant K is obtained by plotting the graph of ln dW over FA naught dx versus ln Ca. From the graph, the slope is actually the negative alpha, while the y-intercept is actually the negative ln K. To do this, a set of data of conversion of reactors X and pseudo contact time W over F naught is obtained from the article by Abbas. So from this set of data, the reaction order and rate constant K can be obtained through the analysis of rate data by differential method. By differential method, the conversion X, and the pseudo contact time W over F is converted to ln dW FA over FA naught dx and ln Ca. So from this data converted, a graph is plotted using Excel to obtain the alpha and K. The alpha and K obtained for the reaction of steam methane reforming are 2.1058 and 4481.44 respectively. For water-gas shift reaction, the alpha is 0.8838 while the K is 3.638. The sizing of both reactors have to be determined in order to obtain the suitable size of both reactors that are required for the production of 30,000 tons per year of hydrogen gas. So, in order to calculate the sizing of reactor, the weight of catalyst have to be determined first by using the data given by Abbas. So, the Moore balance equation for the packed bed reactor is used in this case, and the reaction order alpha and the rate constant K that have been obtained from the previous section are also used. Energy balance have to be performed in order to obtain the equation of temperature that varies with X, because in this case this is not a non-isothermal reactor, which means the T varies with X. So in this energy balance section, the activation energy has to be known in order to do it, to perform the energy balance. So the activation energy that involves in this calculation is actually obtained by the article by Abbas. As the reactor is a non-isothermal reactor, the method of Levenspiel plot is used for the calculation of the weight of catalyst. So the weight of catalyst calculated for the SMR reactor is 13634.08 kg, and the weight of catalyst calculated for WGS reactor is 246422.08 kg. So from the weight of catalyst, the volume of reactor can be obtained through the formula of WK equals to bulk density multiplied by volume of reactor, which is W equals to rho V. Since the bulk density of catalyst is not given, while the solid density of catalyst is given, we have to use the formula of rho B equals to rho C 1 times 1 minus bed porosity in order to obtain the value of bulk density, which are used in the calculation of volume of Richter. So the volume of Richter calculated from the formula stated as 12151.59 dm cube and 219.63 m cube for SMR and WGS Richter respectively.
Other than that, there are several parameters that we can change to increase the conversion of reactant. The first one, temperature. According to Abbas, Dupont and Mahmoud, temperature has a positive effect on purity and yield of hydrogen up to peak value corresponding to complete CH4 conversion. By increasing the temperature, we increase the W/F ratio and the conversion of CH4. This can be seen from the graph below. Next, steam to carbon ratio, S/C. Steam to carbon ratio, S/C, plays a significant role in the overall performance of our process in the packed bed reactor. This can be another strategy for us to maximize the selectivity and yield of hydrogen production. Based on Abbas, Dupont and Mahmoud, the higher the S/C, the higher the overall conversion of CH4. This can be seen on the graph below. The other way to maximize the production of hydrogen is by altering the concentration of the catalyst, because the concentration of the catalyst will directly affect the reaction time of steam methane reformer reaction. The higher the concentration of the catalyst, the shorter times we need to produce our targeted product. This also will save the cost of production 30 tons per year of hydrogen.
Assalamualaikum warahmatullahi wabarakatuh. This is for separation process. As for separation process in particular, adsorption is rooted as the most suitable separation process in H2 enrichment unit as part of process of producing hydrogen from natural gas using steam methane reforming. There are four objectives in separation process. The first one is to identify the most suitable adsorbent to be used. The second one, to acquire the type of dissolution isotherm. The third one, to design adsorption tower including MTZ, diameter and total height of adsorption column. The last one is to analyze strategies to achieve 99.9% of hydrogen production and desorption or regeneration process. So we go to the type of adsorbent used. So the adsorbent must have, first, high selectivity and absorption capacity for carbon dioxide. Second one, adequate adsorption or desorption kinetics for carbon dioxide at operating conditions. And the third one is stable adsorption capacity of carbon dioxide after repeated adsorption or desorption cycle. So we have two types of adsorbent right here, which is the activated carbon and also the 13X zeolite pellets. So from the table shows that the difference of the two adsorbent, which is for the particle density, particle size, particle porosity, micropore volume, average pore diameter, and BET surface. Based on table, zeolite 13X offer highest adsorption capacity of gases such as carbon dioxide, carbon monoxide, methane, and activated carbon provide lowest capacity at temperature ranging 25 to 650 degrees C and pressure up to 2000 kilopascal. From figure 1, all isotherm curves exhibit common behavior regardless of temperature. The amount of CO2 adsorbed on the adsorbent increases very rapidly with the increase in equilibrium pressure over the low pressure range, and it tends to stabilize as the pressure continues to increase. The isotherm were fitted with a dual Langmuir model, and the parameters are available in literature. The single component isotherms were used in the theoretical expression for prediction of the multi-component behavior. The rapid increase in the isotherm curve demonstrates the proper range of equilibrium pressure that promotes the majority of adsorption activity. This is important information that can be used to identify both adsorption pressure and regeneration pressure in the pressure swing adsorption process. The stabilized amount of CO2 adsorbed in the curve shows that all adsorption sites are occupied by CO2 gas, which represent the capacity limit of the adsorbent at the particular temperature.
So, upon deciding the type of adsorbent that we're going to use for our design, we moved on with the design itself. So, we begin our designing with starting off with the breakpoint time as well as the mass transfer zone. So, based on the article that we have referenced, the article provided us with an experimental breakthrough curve for CO2 adsorption in the simulated towers. And based on the simulated values, it has been found that the breakpoint time, TB, is given as 2250 seconds. The height of adsorbent has been given as 0.87 meters, and the height of unused adsorbent HU and B has been given as 0.174 meters. So, since these are all simulated and experimental values, we needed to do relevant calculations for scale-up purposes. And based on the data that has been provided from the curve, the breakthrough curve specifically, and also the article itself, we have done a series of relevant calculations using relevant formulas that we have learned, and we have found that the new total height of adsorption tower for scale-up reasons is 4.924 meters. Hence, our calculation has proven to be accurate since these are the scale-up specifications that has been provided in the article itself, which says that the tower height is equivalent to 4.924 meters, the column diameter is 0.021 meters, and the mass of adsorbent that has to be used is 0.176 kilograms. So moving on to the strategies to achieve 99.9% of hydrogen production, our group has suggested the following strategies. The first strategy is to use longer bed length with reasonable breakthrough time and cost. A longer bed contains more adsorbent, which allows longer online time before regeneration is needed. Moreover, bed utilization efficiency increases with bed length because the unused part becomes a smaller portion of the overall bed. Hence, the longest bed length has to be chosen and one that provides reasonable breakthrough time, pressure drop, and cost. Moving on to the second strategy, that is the purge and depressurization strategy. The proposed PSA sequence increases the H2 recovery by introducing a purge step, which is one that uses a recycle of CO2 rich stream and a pressure equalizing step. The H2 recovery from the syngas can be increased over 98% by providing a sufficient purge flow of syngas. The bed size and the energy consumption for the compression of CO2 rich gas are much smaller than those of other PSA processes that have a CO2 compression system to increase the product purity and recovery of H2. The third and final strategy is to use the electrochemical method. The separation of uncharged species in a typical membrane process is driven by a chemical potential gradient. General membrane separation depends on the pressure gradient to drive one component of the particular mixture. The electrolytic transport of hydrogen in the form of protons across a slate polymer electrolyte in an electrolysis cell is how this method works. Through the supply of direct current, hydrogen can be electrochemically transported across the membrane, and this in turn brings about higher purity of hydrogen.